Итак, у нас пришло время очередного доклада. Выступает Piotr Jarmuż.
Now we're meeting Piotr Jarmuż, hacking with Postgres 11 PG threads. You are kindly welcome. Greetings. I must say that I was studying Russian in Grundschule, in the school, but I can not make it in Russian.
Okay. Hello, welcome to my session. I hope you enjoyed PGConf.Russia. So far, it's lots of great stuff, and I hope you will not be bored during my presentation. So, hacking with Postgres 11 PG threads. This presentation is going to be about writing extensions in Postgres, writing PL, PGSQL, and C code running inside database. And my slide will be accompanied by a lot of demos. I have a vagrant project running 2 virtual machines with Ubuntu and Postgres 11. So this is the agenda. I leave this page on, and I will tell you some few words about me and my company. So I started my career in 2001 as a C, Java, and Perl programmer, and was working a lot with databases, but initially I hate databases because it was slow and showstopper for killer applications. Until in one project I was asked to stand on the other side and manage database. And it happened to be evil Oracle, but it was a very great experience, and I fell in love with the databases and data in general. So right now I am working as a senior data engineer for a company known, Polish company Allegro.pl for 9 years already. And this company is an online marketplace. It's the 6th biggest in Europe. It was recently bought by it was part of the Naspers, together with Małatok, Russian, and Mail.ru. And it was sold by Naspers to the Mid-Europa, Sinven and Permira for $3.2 billion 2 years ago. Our company has 20 million users, and we are an on-premise company. We have 2 server rooms in Poland, but management decided we have to go cloud. And because of our profile, we have chosen initially Amazon for our cloud deployment, but because of our profile, Amazon is our future competition. So we are now going to Google. And having 20 million of users, you can imagine that they will produce quite a lot of data. So our database infrastructure is quite extensive. And the history is that we started with MySQL. Well, it wasn't enough. So the company made a contract with Devil Oracle, and we entered the Oracle contract. Until we found how much it costs, until we found how many license traps are set for us. And at a certain point, 5 years ago, the company decided it is dangerous for our mission, so we decided to ditch Oracle for something else. At first, we tried NoSQL, but you might imagine that NoSQL is not the answer. So finally, the Postgres. And 2 years ago, we started migrating our data to Postgres, and I am happy to announce you that this has been chosen as our default architecture for future deployment. And if I were to describe my company in one word, it's like Amazon plus eBay scaled down to a small country like Poland. So basically, Amazon is not existing anymore. It's very popular, like Yandex in Russia, for instance. And okay, so let's go to the real presentation. First, I will tell you the digression, how developers perceive modern relational database. They usually think that it's a dumb data store with tables. They can throw selects at it, and expect results from it. But it's not really the case, because any modern self-respecting database is highly extensible. And Postgres is a shining example here, because As the only one database on the market, it offers like two-dimensional extensibility. So you can create language, and within this language, create procedure. And the Postgres default language for database development is PGSQL. It's very easy to program because of its how to access data tables, how to integrate selects with control structures. It's a fully fledged procedural language which supports control structures, exceptions, and the PGSQL has several incarnations. You can have functions, and since 11 procedures, which is important, so far we didn't have procedures, and triggers. And the distinction between functions and procedure is that function runs within the transaction started by the caller, and procedure can manage its own transaction. This is very useful. For instance, if you had, before 11, if you had some archiver job, you had to do it from outside database. Now, you can write using PGConf, for instance, you can write archivers directly inside database, and it can manage the archivization using chunk-wise, commit by commit. And of course, there'll always be a way to write extension in C, because it is written in C, but since version 9.6, it's been much easier than before, because you don't have to recompile this from source code. So why would you use stored code inside database? There are several benefits for this. First of all, it's reduced network traffic, because the code is running as close as possible to data. So there is the smallest possible latency. You cannot have any faster. It offers encapsulation, so you can wrap around the user code in a well-defined interface. And in future, for instance, change the implementation, rewrite the query, so without application knowledge. Also the security, because you can hide direct access to developers or users and force them to use stored code. And okay, there's quite a number of built-in functions in Postgres. There will be thousands for them. Many of them are used for string manipulation numbers, also for administration management, and there are tons of extensions which add another host of functions. And if it's not enough, you can always go down and write yourself some extension, which I have done in this demonstration. If you want to learn how to write for programming server programming or writing stored procedures, there's a lot of resources online. I recommend official Postgres documentation with links shown below. Okay, now execution context in Postgres. So Postgres is multi-user and multi-processing environment, but from the point of view of database developer, you have only, from the point of view of a CLI, a PGSQL procedure, you have only one context of execution, and you can do whatever you want within this, but that's all. You cannot have abstractions like Java programmers have. They can create threads and multi-threading. You would have to, again, go outside of database, write your Python or Java code, and make this parallel outside. So I like threading, I like Postgres. Postgres is a powerful computation environment, so why not marry them? So I've sat down and wrote an extension, it's called PGThreads. It implements very simplified API from POSIX threads, which has 4 primitives. One is called create thread, which takes a name. Name is a unique handle for the thread. Maybe I should create some other mechanism like uniquely created ID, but it was just the first approach, so I just labeled the thread with a name. The thread has a thread procedure, which is like a main entry point for the thread. It will be executed once the thread is started. And there's also mysterious parameter hostname. What is the default? No, I will tell you what it does later. So once the thread is created, you can start it. When it's started, it starts running independently from the calling thread. So it gives you the appearance that you have parallel threads. Then, while the thread is running, the calling threads can synchronize with it using join. So you can wait for it until it finishes. And finally, you clean up after this thread, and you call destroy. So some details about implementation. So it is using a libpq client library, asynchronous query execution, and exposes the thread state via regular table thread list, which shows you the currently running threads in the system. And while you have been perhaps expecting that I hacked the core source code of Postgres and make it magically that PG backend program will start be multi-threaded. No, it's not the case. I'm not, because I would say that core developers would be very much against it, because arguably the model of accessing data used by Postgres is the best. It has one big shared memory area and lots of processes that attached to it. It is safe, because if there is a bug in the code, only one session is affected. If, on the contrary, if you have MySQL, it's one big process with many threads, and if you use MySQL, you perhaps had the situation that you had segmentation fault, and suddenly the whole process is dead, or not usable. Okay, my thread has had three states. It's created, running, and finished. And because the PG backend process is like container, so there's natural separation of local variables, local temporary stable. They are private per thread. So the only way you can share data between threads is using the regular database tables, because you are running inside the database, it will be a natural way. So it's time for demos now. Okay, I will just show you. Oh, let's go. Let me see, maybe. Okay, I don't know if it's visible, it's very small. Okay.
Go on.
Once again, the example creates one thread, and I want to do it step by step, calling these primitives. So the function is called create thread. It's given name, and this is the PG sleep. It's a name of the thread procedure. So then you can the thread list. You see that the thread is created. The name of the parameter, its state, the host name where it is created, and timestamp when it was created, and also the connection ID, which is actually the backend, Postgres backend, which implements that container. So let's go next. Next is we can start the thread. So from the thread procedure, you see that it's supposed to sleep for 10 seconds, so we can see how it changes its states. Okay, so it's now running. I can just simply, I don't do anything, just refreshing the state. Oh, okay, now it's finished. And you can see that there are some new attributes. So it has now the end of the execution and the exit code. By default, it's 0 as a success. If there was some exception, then runtime for this thread will catch those exceptions and store them for the calling thread, and it can use the join thread to collect the information. So it was the exit code 0, so right now the thread is ready to be destroyed. And after it is destroyed, it disappears from the system table. Okay, let's have another example. Okay, this is the function that implements simple idle loop. Any number of loops, so we can see that it's actually doing something on the operating system state. So right now we will simply create 2 threads and run them in parallel, and we will also run top on the operating system level. Oh, sure. We can see now 2 processes, Postgres processes having got 100 CPUs. Maybe one more time because. Okay. Kurwa. So anyway, so it's possible to create threads, run them independently from the main thread. This main thread can do something else. Usually there is a threading paradigm programming that you have one dispatcher thread and a bunch of worker threads, and dispatcher thread has some work to do, and it distributes this among the workers, and supposing that you have enough execution resources, the work is hopefully done much faster, and the dispatcher thread can collect the information and display to the user. This is the idea of threading. And right now, I have this threading inside the database. So it's actually giving me developers a very powerful abstraction of doing things. Okay, let's go back to the presentation. So the thread needs to communicate. So by default, because they run in the database, they can use database tables. But because Postgres has this MVCC, everything is against me today. Postgres has this MVCC, multi-versioning currency control, which is a very good thing, but it actually makes it harder for the threads communication of threads or session in generally, because they have to wait till the transaction is ended. There is no way in Postgres to use non-transactional IP for communication. You could use actually something like PG advisory logs and flat files, for instance, but it will be not a very good idea, so I decided to write extensions that implement just that. And if you happen to know Oracle, that perhaps you recognize this is like a DBMS pipe. It's called PG pipe here, and it's based on abstraction of pipes in Unix, so it implements point-to-point communication between processes, threads, whatever, and it is not bound to the boundary of the transaction, so you can actually communicate without necessity to commit. And there are private pipes and public pipes, and there's blocking and non-blocking mode with timeout. And those messages in the pipes are not persistent, so whenever database restarts, they are lost. So because it's not transactional, it makes sense not to persist them. And it uses dynamic background worker process Maybe I could have implemented it directly in the shared memory, but I'm not, at least right now, knowledgeable about Postgres internals to mess with shared memory, so I decided to follow easier path. Background process is something that appeared in Postgres 9.6, I think. It lets you provide your own code and run a process, something like on a similar level, like wall writer, like postmaster. That only difference is that it runs your own code. And this is the pipe server, so it keeps those pipes in memory, and each pipe then has a FIFO of messages. And the session can use it to communicate, and again, demo, I hope they're working. So, again, I need 2 sessions. And I have an example for this. So one session will prepare the message and I will send the message. And this is asynchronous, so it doesn't have to wait for anything, just sends, and the message is in the pipe. You can, again, the background process exposes the pipes in another table, which is called yeah, you can see there's the name of the pipe, and it is private. It's not private, so it's implicitly created, and the count of the message is 1 in it, because we just have sent a message here. So in another session, we can use the code like this and retrieve that message. So what the code does, first of all, there are several procedures that you can use to pack basic data types, so the string, integers, and doubles. It prepares kind of structure. And finally, when the structure is ready, you send the message to the pipe, and the receiver of the pipe uses unpack to actually retrieve the numbers. And if the receiver starts first, it will wait for the message, the 10,000 milliseconds. If message is not there, it will unblock. So we can wait this many, yeah. But if I send now the message, it will get the message. Yeah, you can see. And okay, and now this is important because it doesn't work. It doesn't need the transaction boundary. So I can start actually a transaction here. Start transaction here. Normally, at this point, I'm turning on the MVCC. Then you wouldn't be able to use tables for communication, but sending pipes work as expected. So I can commit or rollback, whatever, it doesn't matter. It can be used, I have another example, maybe that's a trivial example. It's kind of client server inside PGSQL. So the server uses a pipe which is called arithmetic and receives messages, and this client sends simple operator and 2 double numbers and expects the result. So I can demonstrate it. So yeah, we want to add 2 and 1. Yeah, so, or we can multiply that or divide. So it can, if you send it an empty string, they should work. So it is kind of communication that doesn't depend on transaction boundaries. Okay, let's go back to presentation. Okay, now it works. There is another way to communicate this transactional API. We can, for using a bulk data, we can use normal Postgres tables. But I have decided to implement yet another Unix concept, the signals. So signals, we have something similar to signals already in Postgres, listen, notify, PG notify, but it has some limitations. And you cannot use timeouts, or you cannot pass some data programmatically or wait for several signals. And I implemented this again as an extension. But this wouldn't be possible before 11 because it does explicit commit inside. So at this point, our communication works. It's now in a database. It's persistent, and whenever there are two concepts: a signaler and waiter. So waiter registers an alert and then waits for the alert until the signaler sends some alert, and the alert is delivered only on commit. So it's not. It's within the boundary transaction. So another example. Okay. One code. This will be the. Anonymous block that registers an alert and waits for the alert for 60 seconds. So, and in another transactions, I will start another session. I will start the transaction. I will signal that alert, but nothing happens here. It's still waiting because it's transactional. I have to commit, and only then it will receive the message. If I did rollback here, it wouldn't know about this, and it would timeout afterwards. So. There's another example. So you can, the waiter can register several alerts, and you can wait on any of them. So I can have one alert for one event, another alert for another event. So I can say the alert number 2, for instance. So the middle one. Okay. And it now retrieves the name of the alert and the message that was associated with the alerts. So one cool application for this, you can, Java one, for instance. I had another example that uses this for that. There is a table, which is called test table, which holds some integers and strings, and there's some Java application. I hope this is stupid, but it's only I'm using only to show you the concept. So what you can do with the Postgres database as a main hub in your application. So this application registers an alert for the changes in the table. So if I do something like insert into test, okay. Oh, okay. So the alert was not was delivered. If I do this with transaction, so another, let's say 2, so it's not delivered. Only after I commit. Oh. So it works even with several instances of this program. And this program has ability to modify the data, so I can delete. And you see, it works the same. So no matter where I change the data, the programs get the notification, two notifications for the same time. This is implemented using this PG alerts inside a database, using Postgres triggers on the table. So whenever something happens on the table, the alert is sent and delivered to the application. Okay. Let's go back to our presentation. And now, putting it all together, so I want to show you how to use this PG thread in practice. So I decided to solve a game because it's a very untypical problem. The game is called Wordament. It is written by Microsoft, very popular with touch devices, so you can play. You actually displays you this board like this, and you use your finger to build a word. And if the word is verified by the program that it's valid, you are rewarded points. And when my friend showed me this program, I thought, wow, it's a great idea for implementing this inside the database. So this is how it looks. And we have solution in single threads. So it uses, it starts with an empty word, and whenever it uses the depth search first tree algorithm and follows any possible combinations and any of possible directions. And whenever there is a match, it adds to the local table, and at the end, it displays the list of found words. So it is dictionary-based, so I can, because Postgres support Unicode, so I can load any language I want. I have it in Russian language, for an example. And so let's play. I'll show you an example. This is, I know. Just let me show you this. I will let it run. Okay, let me show you now what it does. The game is represented by string. The string has 4 segments. Each segment is separated by white space. Each segment represents 1 row. It has the letters, and it uses the existing dictionary and follows all of possible words and gives you the solution. So for instance, this has, in English language, has 275 rows. So let me show you Russian. So I hope you can verify that my solution works. Because the algorithm works on a view, I can redefine the view to Russian, and I have some game instance with Russian. Okay. So maybe you can verify if you. Perhaps it's not easy to verify whether this game is working in Russian. But anyway, Postgres works out of the box without with this. So the single solution, and if you, and this it shows the longest solution here. And well, when you look at the game, it has inherent parallelism, and because in general, game theory is a branch of mathematics, and it has natural ability to partition problems. So you can, for instance, have one game of chess and simulate hundreds of thousands of sessions. It's called embarrassingly parallel problem. So in our example, it is we are running search trees, and we have in our original board 16 initial routes. We can run, in theory, 16 search trees. So right now, why don't use our threads for showing we can solve the problem faster? I use parallel version. The parallel version is different only that it accepts another parameter, which is number of threads we want to run it with. So we can run it. I have to switch back to English for this. And again, this will be parallel version with one thread, so it should take about the same time as English version was 2 seconds. How about 2? Oh, it's much faster, it's twice as much. How about 3? It's still faster. How about 16? It's not much faster because this is virtual machine, it only has 2 CPUs, so it will scale linearly up until you exhaust your resources. Now, what I wanted to tell you that how does it work? I will show you the source code because it actually represents this paradigm I told you before. This is the version. I don't know if it's seen. Maybe I should. Okay, so maybe if you have time.
У нас осталось буквально пара минут на...
We have only 2 minutes left for 1 or 2 questions. If you want to ask a question, you may ask in Russian, and we have simultaneous translation. Do we have any volunteers? I suppose we don't have questions. Oh, no, still, we have a question. Greetings. Thank you very much for your presentation. My question is, if we open a new connection to Postgres and start 2 threads and then close this connection, what happens with threads while they are not joined, before they are not joined?
You must answer it here.
So your question was, what happens if I create 2 threads, let them run, and I don't join them?
When I close the connection where the threads are created.
There is a cleanup procedure for this. So whenever you start another thread, it uses a pgstat join, a pgstat table, and this thread list table, and joins. And if you see if there is a match, it means that the thread is still running. The connection is there. If it's not, it does clean up automatically for this.
Yes, okay, thank you.
Что ж, я боюсь, у нас совсем...
I'm afraid we don't have time for the discussion now, and you can meet in the hall. We have 5 minutes more to be prepared to the next presentation, so now we have a pause. Thank you very much.